Hey everyone, welcome back to Everything Mathematics. In today's lesson, we are going to put into practice everything that we have learned so far when it comes to trig, particularly all the trig identities that we have developed. I have a lot of videos where I derive the main identities from scratch. I will make sure to link those videos in the description below. So in this lesson, we're going to put all of these identities into practice in order to prove other type of identities. I'll walk you through two examples step by step so that you see exactly how that works. Let's get started. To start, we will assume that we have already some prior knowledge of identities, particularly that we are very familiar with the Pythagorean identities. Sine squared plus cosine squared equals 1, and 1 plus tangent squared equals secant squared. Also, we will assume that you are familiar with the reciprocal identities, these three over here. These are the ones that I'm going to be using in this lesson, and that you are familiar with these two double angle identities, the double angle identity for sine and for cosine. Here I have some useful tips that I want you to keep in mind when proving identities. These tips can really help you figure out what sort of steps you should take whenever you are presented with an identity. For example, number one. Number one says that when you have an identity and you're trying to prove that the left side is equal to the right side, you should pick the side that seems more involved, the one that seems more complicated, because this is the one where you will be able to simplify by applying algebraic operations in order to obtain the other side. So pick the side that you feel is more involved because it will give you more opportunity to work it out. Number two says that you should re-express all expressions in terms of basic trig functions. So make sure that any expressions that may involve cosecant, secant, or cotangent that you may want to consider and that you may want to re-express it in terms of sine, cosine, or tangent. Number three says that if you have fractions and you are adding or subtracting, consider getting a common denominator. Number four says, well, if you can use identities to replace, to substitute some expressions, then do that. Take advantage of your identities to simplify. And I'm going to show you in the examples exactly what I have in mind there. Number five says that sometimes you may want to multiply the numerator and denominator by the conjugate, right? The idea of multiplying by conjugate. So that's going to be very helpful in some of the examples here. And number six, factor, factor, factor. Whenever possible, whenever you see a quadratic, try to factor the quadratic. Whenever you see a common factor, try to factor it out, and so forth. So here is the very first example. They are asking us to prove this identity right here, that this left side is always equal to the right side. And I think that is pretty clear here, that the right side seems to be more involved, seems to be more complicated. So I'm going to go ahead and get started with the right side. Okay, so in this particular case, we are going to have, I'm going to write the right side here, cosine of 2x minus cosine of x, all this divided by sine 2x plus sine x. So this is the right side. Now I notice that right here, I have cosine of 2x and sine of 2x. So perhaps I can use that double angle identity. So I can now replace these terms with an identity. Now, in the numerator, since I have cosine here on the right, I am going to use the identity, the double angle identity for cosine that only involves cosine. For example, this is what I have in mind. For this one right here, I'm going to use the one that says that cosine of 2x is equal to cosine to 2 cosine squared x minus 1. So I'm going to use that one. And then for the 1 here in the bottom, the fact that sine of 2x is equal to 2 sine x times cosine of x. So let's go ahead and do that. So in the numerator, we're going to have 2 cosine squared x minus 1. And then over here, minus cosine of x. That was already there. And all this will be divided by 2 and then sine x times cosine x plus sine x. Then I want you to notice how here in the numerator, I have an expression that seems to be a quadratic. In fact, I'm going to go ahead and write it in descending order. So 2 cosine squared x minus cosine x. Practically, I'm taking this term and I'm placing it in the middle. And then minus 1 will be at the end. And all this will be divided. Now I want you to notice how here in the denominator, I have a common factor. I have sine x and sine x right there. So I can actually factor that out. I can write this expression as sine x. And then inside of my brackets, I'm going to have 2 cosine x plus 1. Just like that. Notice that if I were to redistribute this, I would have this times this, and that's how I will get the first term. Sine x times 1, that's how I get sine x. So that looks great. Now, in the numerator, I have my quadratic. So in order to continue simplifying, I'm going to have to factor this quadratic. So practically, this is what I have right now when it comes to the quadratic. Imagine that I replace cosine with another variable, u. So imagine that we say, let u equals cosine of x. That means that I can rewrite the quadratic as 2 u squared minus u minus 1. And then I can factor this quadratic separately. By substituting cosine with u, the quadratic feels so much friendlier. It looks friendlier. It seems easier. So I can factor this as 2u, then u here, plus minus 1 and 1. So now that I have factored, I can come back and replace u with cosine. That means that we would have here, so these are my two factors, and I would have 2 cosine x plus 1, and here cosine x minus 1, and all this will be divided by sine x times 2 cosine x plus 1. And then I want you to notice that I have two identical factors, one on top and one below, which means that I can nicely cancel those factors out. And when I do that, let me continue here on the right, I will have cosine of x minus 1, all of this divided by sine x. So I cancel my factors, which is what I wanted. I wanted to have some sort of cancellation, which really means I'm simplifying my expression. And now I'm going to take a look at the other side to see if I match. And then just by quickly looking, here is the left side, and this is what I have. They still don't look identical. That means that I can continue doing something else. I can now take this fraction and break it apart. For example, I can have cosine x over sine x and minus 1 over sine x. This is like saying something like this. If I have a fraction, let's say a plus b all over m, I can separate the fraction into two separate terms over the same denominator m. So a over m plus b over m. That's what is happening there. And now I want you to notice how cosine over sine is equal to cotangent of x. And notice that 1 over sine is equal to cosecant of x. And now when I look at this expression here, and when I look at this left side right here, let me circle that. They are identical. So then that means that the identity is true. That means that we proved it. We started with the right side. We never assume equality. We did quite a bit of algebra involving other identities in the process, involving factoring in the process, and then we ended up beautifully with the other side. So then that means end of proof. The identity is true. We're done. Now here we have another one, another identity that they're asking us to prove. Now, in this case, both sides are equally as involved. I cannot really tell which one is easier, which one is harder. So I'm just going to pick one and I'm going to try it out. I'm going to try to work it out and hopefully I'll be successful. But if not, then you are welcome to start over with the other side, work it out and see what happens. So in this case, I'm going to start with the left side. Honestly, no particular reason. I'm just going to pick the left side just because it's there first. And then I remember that I have an identity for tangent squared, a Pythagorean identity, in fact, that connects tangent squared with secant. This identity says that 1 plus tangent squared of x is equal to secant squared x. And then I can take this identity and I can isolate tangent squared. So I can write that as tangent squared x equals secant squared x minus 1. We're taking this 1 and we are subtracting it, so that will move it to the other side. Now, what I am going to do here is I'm going to take this expression right here and substitute it in the numerator of my fraction. Look at this. Now we're going to have very nicely secant squared x minus 1 divided by 1 plus secant of x. And this is why the left side was actually a nice side, because immediately I saw a connection between tangent and secant through this Pythagorean identity. Then I noticed that here I practically have a quadratic, and as soon as I see a quadratic, I think of factor, factor, factor. So this is practically, imagine that you have something like a squared minus 1. In a sense, it's a difference of squares. You know that you can factor that as a product of conjugates, a minus 1 times a plus 1. So that's what I will do here. We're going to go ahead and factor this as secant x times secant x plus minus 1 and 1. And now we will divide all this by 1 plus secant of x. I want you to notice here that having 1 plus secant x is the same as having secant x plus 1. Same thing. And now what is so nice about that is that I can very nicely cancel these two factors. I'm going to go ahead, cancel them out or divide them out, and I will end up with secant x minus 1. Now, when I take a look, this is what I have, and I look at the right side, I still don't see a match. That means that I need to continue working this result here. And I can do that by thinking about the reciprocal identity, because I want a fraction. I have a fraction on the other side. So I know that secant x is the same as 1 over cosine x by reciprocal identities, and then minus 1. And now I can get a common denominator. So I'm going to put this over 1, and I will multiply top and bottom by cosine of x. And when I do that, I will have a very nice common denominator, cosine x, and then 1 minus cosine x in the numerator. And then notice how beautiful. This here is identical to the other side, which really means that this is the end of proof and the identity is true. All right, everybody, I hope that you enjoyed this lesson. It is actually quite fun to take all of these identities and play with them, and with your notion of factoring, getting a common denominator to get the end result. I mean, sometimes it will be tricky. Sometimes we're going to hit walls. But remember, try the other side. Try things around. Don't give up. Mathematics is like sports. Practice, practice, consistent practice. Until next time, bye-bye.